1.4 covers transformations of cubic and quartic functions. So before we get into cubics and quartics, what I'm going to do is I'm just going to talk about something simple like quadratics. Okay, so let's do a little bit of a review of grade 11. Here is a quadratic. I can tell because there's this little 2. And basically what I have to do is I got to graph this thing. I'm going to tell you right now that within this entire video, I'm not going to graph anything. In fact, I'm just going to show you how you would set up the steps before actually graphing, because graphing after this would be simple. What I like to do is I like to do mapping notation. So mapping notation is where you take all of the original x values. So I usually choose some negatives, a 0, and some positive numbers. And then I would take the original graph, which we said was an x squared graph. So what I'm going to do is I'm going to take all these x values and I'm going to square them. So I get all these y values. Now this is mapping notation because we take these values and we apply any of the transformations to them. So the transformations I can clearly see in this step, but I actually couldn't see them very well in this step. Whatever's inside the brackets usually needs to be factored, or else a lot of people would normally think that this goes to the left one and they would actually be incorrect. So what you want to do is you want to factor out whatever the coefficient is in front of that x. And that goes right in front as your k value. Okay, so this is your horizontal stretch or compression. And what goes in here is whatever these two are after they're divided by that k value. So if I divide this by 1/3, I'm just going to get x. And when I divide 1 by 1/3, I'm going to get 3. Now if you ever need to mentally just check that, you can do so. Just take the 1/3 and kind of in your head multiply it back in and see if you get this. If you do, you got it correct. If you don't, you probably made a mistake. So now I can see that this actually doesn't move to the left one, it moves to the left 3. Okay, all the other components are easy to see as well. So what we want to do is apply probably the easiest components first, which are the verticals. So that's these two right here. Now those two vertical components will affect obviously the vertical numbers, which are your y values. Okay, so this is a vertical stretch by a factor of 2, a vertical reflection over the x-axis, and a vertical translation up 7. And they affect your y values exactly as you see them. Okay, so something like this. So all the negative 2's go in front, all the positive 7's go at the back, and then you're just going to calculate your new numbers. Negative 2 times 4 is negative 8, plus 7 will give you your new number, negative 1. Okay, so right there. Then you're just going to calculate the rest. So these are your brand new transformed y values. Now anything within here, actually I like to think of this as kind of almost like a house. So anything within the house is your horizontal components. Okay. Now why I like to think about this as a house is because I kind of like to think of it like a fun house, like Topsy-Turvy Land kind of fun house, where nothing is exactly as it seems. So even though you have a 1/3 here, you're actually going to affect your horizontal components by multiplying by 3. So notice that you take the reciprocal of this and you multiply it and it goes in front. So these are all 3's. Then instead of adding 3, you're going to subtract 3. So the horizontal components are always opposite of what you would think, and that's why I like to think of it as a topsy-turvy land. Okay, so what you're going to do is calculate your new x values. 3 times negative 2 is negative 6, minus 3 is going to be negative 9, and those are our x values. Okay, now these are your new transformed coordinates, and then you're just going to graph those on a graph and connect all the dots with a line. Okay, so this is your new quadratic function. Now that was a quick review, and if we talk about cubics and quartics, everything is exactly the same. You still have your a value, which means the exact same thing it did before. Your k value, your d value, your c value. So these two are your translations, your up, down, left, and right. These guys are your stretches and compressions, but talking about verticals and horizontals. And then these guys are also, if they're ever negatives, are your reflections over the x-axis and y-axis. Okay, so this is basically saying the same thing. All the transformations stay exactly the same, nothing changes. The only thing that changes is your exponent. So let's just take a look. If your exponent is a quadratic, it's just going to be a 2. If it's a cubic, it's going to be a 3. Quartic is going to be a 4. But notice that none of the letters in any of the positions actually change. They're all the same, and they mean the exact same thing for these new polynomials. Okay, so let's take a look at a small example. I have something right here as an already factored quartic function, so it's a quartic, we can tell right here. Specifically with even degree functions, they're kind of like parabolas where, remember, these two numbers would be your vertex. So a quartic does sometimes look like a parabola, and that vertex right there is found the exact same way. So you take your -4, and remember, funhouse, so opposite of this is a +4. But whatever's outside of the house is taken as is, and it's going to be a +10. This is the vertex for this quartic. You have the axis of symmetry, which is the first number of the vertex. Okay, and then we always have to write x equals 2 because it is a line, so we have to write it as an equation. This is a minimum point on the quartic function, and it's a minimum of the last number in your vertex, so a min of 10. If we take a look at an example of a even function, an even degree function, what we can do is we can take all of the different transformations, and remember that we actually have to factor out that bracket first. So we're going to factor out the 1/2, and it's going to go right there. And this 1 is going to change because it's going to be divided by the 1/2, and it's going to become a 2. So the quartic, so the 4 is on the outside, and the 7 and -1/4 don't change. Okay, so what's going on here? Let's list all the different transformations. There is a negative here, so there's a reflection in the x-axis. The 1/4 is a vertical compression by a factor of 1/4. There is a horizontal stretch by a factor of 2, so the opposite. Also the opposite here, you're going to see a left 2 units. And then this guy we take at face value, which is up 7 units. Okay. So what I'm going to do is I'm going to start to create, because they're going to ask me to graph later, which again, I'm not going to in this video. I just want to show you mapping notation. We're going to create the table of values. All of your x values, again, I'm using the exact same numbers I used before, but your y values are going to change because the base graph is a quartic. So I just took all of these guys and put them to the power 4, and I got these guys. Any of the red are your verticals, which will affect your y's. And then notice that the numbers, again, they don't change. Whereas the horizontal components, because they're in that fun house, they're going to be the opposites. So this is going to be the reciprocal, which is a 2. And this is going to be a -2. So what we do is we calculate our new coordinates right over here, and then we just graph them. What I could do even before I graphed is I already know that this is a quartic function, which means that it should extend from quadrant 2 to quadrant 1. But since it's a negative leading coefficient, it's going to be upside down. Even so, your domain should be all real numbers because it opens up wider and wider forever. But you will have that max because it is an upside down parabola shape, and therefore you'll have some sort of a range restriction. So the highest you could possibly go is 7, and then you'd have to go anything lower than that. I could tell you, even before graphing, that you have a vertex of -2 and +7, so right here. You can also tell that this is going to be your axis of symmetry. Okay, remember the x equals 2. And then this guy right here is going to be your max or min, and we know it's a max because it's a flipped parabola shape. Let's now just briefly talk about an odd degree function. Okay, so we're going to do the exact same thing. We're going to take this guy, we're going to factor it. You're going to factor out that -1, and you're going to be left with not a +6, but a -6 instead. I'm going to prepare my table of values. by taking all my x values and cubing them because it was a base graph of x cubed. So I have all these numbers right here. Now, I'm going to apply any of my transformations. So I have a vertical stretch by a factor of 2, and I also have a vertical translation down 3 units. So I'm going to take those as face value, and I'm going to put them right on the vertical component, which is my y. Any of the horizontals I'm going to flip to something opposite. So instead of a -6, I'm going to put a +6. And this -1, even if I flip it upside down, is still actually going to be a -1. So I have negatives in front of all these guys. And I'm going to calculate my new coordinates, and then I'll graph those and join all of the dots. So in terms of the domain and range, we should expect, because it is a cubed graph, it should look kind of like this shape. And there's a positive leading coefficient, which means it didn't actually flip at all. So we're extending from quadrant 3 to quadrant 1. And this guy is getting taller and lower forever, and then also wider forever. So your domain and range are going to be all real numbers. Notice that, again, just wrapping up this video, everything is exactly the same as it was when we talked about functions in grade 11. All these transformations do the exact same things with higher degree polynomials.